This episode is brought to you by Brilliant.
Our progress in the field of rocketry this last decade has been amazing, but to reach a future in which millions can travel to and from orbit every day, we will need freeways and train tracks to space itself. So today we are going to be looking at a space launch system, the Tethered Ring, that is a cousin to the Mass Driver, Orbital Ring, and Lofstrom Loop, three of our favorite active support launch systems. Now each of those has its own episode in our Upward Bound series that you can watch for details, and it seemed right that the Tethered Ring should get its own episode too. It's a fantastic idea for hanging a non-rocket based launch system in the upper atmosphere that could make launch cost to orbit around Earth as cheap as air travel around Earth, and indeed could make travel around Earth a lot faster and cheaper too. If you haven't seen any of those episodes, they are not prerequisites to understand today's topic, but a basic understanding of them is helpful to understand how the Tethered Ring works, as is an understanding of active support. So we will cover them briefly today as a prelude to the Tethered Ring. It might be helpful to think of the active support in a Tethered Ring as a system for simply keeping our ring rigid, something that a potential supermaterial might allow too. So while the coolest thing about the Tethered Ring is that it can be built on the Earth's surface entirely with present-day technology for a reasonable cost, for our sci-fi writers out there, it actually represents something you could have hanging on a planet without maintenance or power needs, if you had a rigid enough supermaterial. This is a ring that hangs over a planet by being tethered to the ground, thus hangs over the ground by hanging from the ground, a somewhat counterintuitive notion that we'll explain in a bit. When its inventor, Phil Swan, explained the concept to me at the International Space Development Conference, I had a facepalm moment at the beautiful simplicity of the idea, and never thinking of it before myself. He and his team, which goes by the name the Atlantis Project, have been developing and discussing it for years, and I'm very glad that SFIA is going to be a venue to help popularize the notion, and I'll be linking to the website for it that has all the deep dives and technical details, and also a very nice app for placing the rings where you want and with various parameters you like. This is a very cool system that would work well on Earth and on many other planets too. Now, active support is seen by some as a technique for emulating supermaterials by applying large amounts of energy, and in the simplest conceptual example, it's like keeping a piece of paper floating by placing over a heat vent on the floor. Indeed, if you anchor that paper with a cord or tether to the vent and left the vent running, it would hang up there forever, and ants could crawl those tethers to the paper and hang out there and build cities there. This is active support. And so would be a helicopter or drone quadcopter that had an electric engine that you anchored to the ground with a power cable from a power plant. We could also do the same with a plane, but we'll need to fly in a circle to avoid breaking that power cable. Of course, if it was flying high and had a railgun or an electromagnetic cannon on it, a mass driver, it could launch things from that altitude, high above most of the air, and the US military has funded studies on the feasibility of launching payloads to space from high-altitude planes, which have concluded that this is plausible from a thermodynamics point of view. Indeed, that power cord could power both the floating plane and the launcher attached to it, and would be a viable space launch mechanism. I don't know of anyone having previously studied or named that approach before. It's one I've played with on and off for some years, and it has probably been thought of before, so I won't claim it and name it today, especially as it's not our focus, nor would it be very handy except for maybe a new colony planet with limited launch needs and a centralized force base, and mostly for cargo that can handle a lot of G-force. Think of it as a planetary slingshot. The topic today will essentially replace that circling plane with a much better static ring, which spacecraft can race along to launch into space at accelerations that humans would find comfortable. Active support comes in other forms too. It's the same concept for a water hose, which is a fairly floppy device, but when we run water through it at high pressure, it suddenly becomes quite stiff and rigid, but not as rigid as, say, a large ring of diamond. Generally, our discussion of active support on this show are for building giant space towers, orbital rings, or even artificial planets, and thus utilize methods for replicating materials stronger than nature seems to allow. The orbital ring, for instance, uses a giant hollow ring around the planet, stationary with respect to the ground and with magnets inside, while inside this sheath a metal ring spins at slightly faster than orbital speed, and we can speed up or slow down that ring with linear motors on the outer, stationary sheath, and we use levitation electromagnets to keep the inner ring from touching the stationary sheath while it is moving around at 10 kilometers a second or even faster. The combined momentum of both objects is kept at what is needed for orbiting Earth at that altitude, a velocity of 7.8 kilometers per second times whatever its total mass is. Total mass for itself, both inner ring and outer sheath, as well as the cargo on it, the ships, the tethers helping hold it in place on Earth so it doesn't wobble or suffer from precession, and possibly solar panels to power it. You use tethers often at an angle to keep it in place and provide transport via cable car up to the ring for people, cargo, and power, and it's an excellent launch location. With very good superconductors and magnetic shielding, this can be very low power. It is easiest to do above the equator, but so long as your tethers are strong enough, you can position your hoop at any angle around the Earth. But it's still larger than the full circumference of the planet, which implies that you need to build it in orbit, which means you need to launch material in low Earth orbit to build it, or mine the material from the moon and then bring it to low Earth orbit. On the other hand, a tethered ring has a smaller diameter and thus can be built on Earth, for example in the ocean around Antarctica or in the Pacific Ocean. These, as we'll see in a bit, are some of the options the Atlantis project team proposes. You can tap power off that inner spinning metal ring, or simply run other electricity up there to magnetically propel a space vessel along the ring until it reaches orbital speed itself and can launch off. The same is true of the Lofstrom Loop, which is easier to think of as a cannon on the ground, firing metal pellets in a big parabola up into space that land far away and get turned around and fired back. And much like the inner spinning ring of an orbital ring, we can build a sheath around this and give ourselves a big launch ramp suspended in the air. We can then either leech power magnetically off the metal pellets or chain or ribbon inside the external stationary sheath, or just run a power cord up to it. Same concept for a space tower, except here we magnetically accelerate metal pellets or bolts straight up, then use magnets at the top to redirect them back down again, which counters the pull of gravity. The systems at the base accelerate the pellets back up again, and on this track we keep a large tower built, which can be impossibly tall compared to what even the strongest of tough compressive strength materials permit. Active support is very good for making things rigid or having great compressive strength, so long as you either have lots of cheap power to run it, or you have a way to minimize the power requirements. One way to approach this is to use superconductors and good magnetic shielding, but the Tethered Ring white paper design proposes a different approach, which is more akin to the technology used in active magnetic bearings, specifically a type of active magnetic bearing called a permanent magnet-biased homopolar linear active magnetic bearing. Don't worry, you don't need to memorize that term. Active support can also, with a little more work, be used to replace high tensile strength materials. This is the strength a material has when you pull on it rather than push on it, or when you hang a weight from it. See our Ring Wars episode for discussion of how, but for today's topic, tethered rings, it is worth noting we have materials that work for our tethers already, like Kevlar or Xylon. Indeed, carbon fiber will do the trick, though obviously super materials like graphene could do it even better if they could be made cheaply enough. The difference is that when we look at space elevators, we are looking at materials that need to hold vast weights up over tens of thousands of miles or kilometers, while alternatively our tethers on an orbital ring, Lofstrom Loop or Tethered Ring just need to hold things for tens of miles or kilometers. Still not easy, mind you, but inside the realm of materials we already have the ability to cheaply mass produce, for a given value of the word cheaply. The basic models of the Orbital Ring, Lofstrom Loop, Space Tower, Mass Driver, and Tethered Ring all cost in the tens of billions of dollars. Active structures also require maintenance, and I usually assume such things parallel highways and bridges at needing about their original cost to build to be spent again over the course of a decade or two to keep them up. and they also need a lot of energy to stay up and to launch spaceships. What's cool about them all is that it takes so much less energy per kilogram launched, so long as you're doing a lot of launching. You knock your launch costs down to maybe 100th what they are now, but only if you're interested in doing about 100 times as many launches a year as we do now, preferably more. Folks sometimes wonder why we don't build these things already if they're physically possible, and that's the key reason. It's like a railroad or the Panama Canal, way cheaper fuel costs once built, but only if you are moving enough freight to justify the initial cost and maintenance. So building space infrastructure makes sense when your space goals are ambitious, such as setting up and supplying human outposts on other worlds, but it perhaps makes more economic sense to use rockets if you only want to launch satellites and build a space station or two in low Earth orbit. Another reason these don't get built yet is because even though the basic physics works fine, like anything else they need prototyping, and often anticipate some technological improvements that would make them way more effective. The Tethered Ring is pretty simplistic and can be built smaller as a test model, so there's less worries of needing multiple generations of expensive prototypes, and it also doesn't require the cooperation of a bunch of different countries to build these prototypes. One problem with the Orbital Ring is that since it does have to encircle the entire planet, even if not at the equator in favor of being tipped at an angle, it still has to pass over a lot of countries and just hang in the upper atmosphere above them. So we assume permission has to be gotten from them to build it. They have good reason to say yes, as it presumably grants them ultra cheap and fast access to both space and everyone else on that ring, but the geopolitics could still be a pain. Alternatively, a full-scale tethered ring can be built and tested many meters below the surface in the ocean, in international waters. One possible location discussed in the patent is around the Antarctic continent. Another, discussed in the white paper, is around the Pacific Rim. In fact, after a tethered ring is constructed and raised, it can be moved to a better location if the geopolitical issues can be worked out, so that it can provide carbon-neutral, point-to-point, international, high-speed transit for the countries that it passes over. A tethered ring is lifted up and held up by its tethers, which can seem a bit counterintuitive. We actually hang it from tethers attached to the ground, which keep it from falling down to the ground. And we do hang it too. We have some visuals to explain this we'll be putting up on the screen, but for our audio-only listeners over on SoundCloud, Spotify, iTunes, Audible, Amazon Music, and others, this might be a bit tricky to visualize. Picture a basketball and a metal hoop just a bit wider than it. This hoop is our normal orbital ring and can be put at any angle. Now shrink that hoop down to be a smaller radius than the basketball. It can be placed on the basketball and it won't fall down and hit the ground because gravity keeps pulling it straight down while the hoop isn't wide enough to finish dropping past the basketball once it widens out wider than the hoop. Of course, this does not result in the hoop hanging in the air, it just rests on the basketball's surface. However, Earth's gravity doesn't point down at the ground, it points in towards the basketball's center when Earth is the basketball. So a big hoop around Earth would just land on the ground wherever, as everywhere is down. Indeed, it would flop to the ground, as even a ring made of pure diamond would be as flexible as a rubber band at this scale, much like our Topopolis megastructure, a giant spinning hollow steel cord miles wide that we can literally tie in knots or loops because it's flexible at big enough lengths. Making our ring rigid is the principal role of active support here, and the only part it is required for. Just as with the orbital ring, we have a hollow tube lined with magnets, stationary with respect to the ground, and inside there will be a big metal hoop spinning at high speed, and much like water in a hose, this will make the object rigid even though it's thousands of miles long. So why isn't the ring falling down? The tether's attached to it and the ground, not space, so it's hard to picture how this is actually hanging in the sky from those tethers. If I ran guy wires up to a hot air balloon after all, those hold it to the ground, but only because it wants to move up. Shut off the hot air or replace a blimp's helium with lead, and it will fall down and those tethers won't stop it. Here's the key part. Earth is curved, and down is not in the same direction everywhere along this ring or its tethers. If you picture a very long tether running from the ground off at an angle, then as Earth curves away beneath it, the distance from it to the ground is going to rise sharply. Indeed, even a straight line running along Earth's surface is going to curve away to great height. This is how the horizon works for light moving in a straight line to your eyes from some distant object. So what our tethers are doing here, as they radiate out from the ring opposite of how spokes of a wheel go, though slightly angled down, is to reach to a distant spot to anchor the ring in a roughly straight line. Since the planet is curved, if the ring falls down, it pulls on the tethers more, thus it cannot fall down. Our ring is held in the sky by being tethered to the ground. It's a really neat trick, and if you're having problems still picturing this, then flip it around and imagine holding a ring or disc from guy wires off the side attached to tall towers. The ring is held up by hanging down from those. This is still the case, it's just that our tethers here are very long and our towers are further away, and the point where they attach is high relative to the ring, because the Earth is actually a little bit inside the ring as opposed to being entirely below the ring. Thus they don't actually need to be up in the air at all. They can be on the ground because of the planet's curvature, and because the ring's size allows it to partially encircle the planet. Of course, for a big ring, thousands of kilometers in circumference, it would droop and stretch all over the place between those tethers, pulled outward where a tether connected and drooping down between two tether connections, so the tethers are forked so they distribute their tensile forces more evenly. Also, that inner spinning ring keeps the outer stationary ring stiff and circular. Much as with the Lofstrom Loop or Orbital Ring, we could use the kinetic energy of the spinning ring as a source of power for a launch or two, sapping speed off the ring magnetically to propel a ship up to speed. Our ring is still in the atmosphere, mind you, so it makes sense to house the mass driver within an evacuated tube and have a fast opening airlock at the end to let the spacecraft out without letting too much air leak in. We looked at this in mass drivers, and a plasma window might be an option too. The reference design for the ring is at an altitude of 32 kilometers. That is far above storms and thick air, so maintaining a near vacuum tunnel around the launch track is no problem, and those tethers also make a great way to move people, cargo, and power up to the ring. So, how big is this ring? Well, that depends on circumference, of course, and bigger is better in this case, as it means your ship can accelerate to higher speeds with a larger turning radius. At the ISDC this year, Phil and his colleague, Ceana, presented us the option of one running essentially around the perimeter of the Pacific Ocean as a circle, with about half its mass in the ring and half in the tethers, but the majority of the cost is in the tethers themselves, which use just over 2 megatons of carbon fiber and roughly cost, in current money, about $45 billion. There's also the transit tube and of course the outer sheath and inner metal hoop. The metal hoop would probably be made from iron, although any ferromagnetic material works. The inner ring just needs to be decently sturdy and able to be shoved on by magnets. The outer sheath can be aluminum, as it's lightweight and decently cheap, and we can also put solar panels on it to power the whole thing. A meter wide over its entire circumference is sufficient. In terms of actual energy stored in the ring, that varies by size, and much like the orbital ring, you can make these much thicker if you want, but the baseline model would have 2 × 10 to the 17 joules running inside that hoop at any given moment, roughly the amount of energy that hits Earth every second from the sun. How often we need to replenish that energy overall is hard to say at this time, but at least many days, so the solar panels or perhaps a handful of modern power plants could do the job, if not less, and you could be doing much of this recharging up power cords on those tethers from the various major cities they connected to outside their peak hours when they had a surplus, or again by hanging solar panels from the ring. Even if we needed total energy replacement once a month, which would require almost 80 gigawatts of power production to hit that 2 × 10 to the 17 joules over a month, that's still not much at the global scale. However, that is a lot of juice, the equivalent of roughly 50 megaton nuclear devices, but it's all spread out over thousands of kilometers, same as car wrecks on a freeway system or a hurricane, and a hurricane contains 100 times the kinetic energy. But it is worth considering what would happen if the ring got wrecked, and whether it would damage things. If it did break, it's not a huge worry. Much like an orbital ring, all the fast-moving parts are either flying off in orbit or burning up the atmosphere like meteorites if it breaks. The bigger stationary segments could just deploy parachutes and fall gently down. I wouldn't say a thick carbon fiber tether falling down is going to be totally safe for those nearby, but it would be nothing compared to a train wreck. And this is what we're seeking to replace here. Of course, a lighter material like graphene works even better and would allow even more safety provisions, but Phil Swan and his collaborators were focused on modern and available materials, and those available in 2015 specifically when the idea was first developed. Phil told me that way back in the 1980s he had been doing simulations of space elevators and concluded that the tethers were impossible. And this was pre-graphene, and he went on hiatus with such thoughts till 2015 at a conference on space elevators. And that's where this idea was first publicly presented. It hasn't been a secret either. I'm a little sad it was around for nearly a decade and this show's entire lifetime before I encountered it. And next week marks our show's 8th anniversary, incidentally. Now again, all numbers are necessarily approximate and in modern values and technologies, but I want to step through some specifics before we close out, as well as looking at more high-tech versions and off-world use. The Tethered Ring reference design's height is 32 kilometers or 20 miles up. That keeps it above air traffic and weather. Transport could be directly up a vertical cable that's 32 kilometers long or at an angle, and the angle does not have to be uniform on this. You also can run cables inward or outward, not just directly down from the tether, which means that you can locate the elevator's terminuses near train stations or city centers if you wish, even if the ring doesn't pass directly over these locations. The default tether is 110 kilometers long or 70 miles. At the anchor point, a tether is on the order of an arm's width in diameter, and it will widen slightly as it gets closer to the ring, much as a tapered tether for a space elevator does. Spacing of the tether's anchor points could be about 45 kilometers or 28 miles between each tether, but because the tethers fork on the way up to the ring, the spacing of the ring attachment points is just a few meters, feathering out to evenly grasp it. We are assuming a transit tube with a diameter of about 12 meters or 40 feet which supports 4 lanes of traffic. The cars that travel within it are 4 meters in diameter and 20 meters long, similar to the fuselage of a business jet, and these cars can switch between collector and express lanes. The mass driver's tube could support space vehicles with diameters of 12 meters or possibly more, which can obviously hold a lot of spaceship or cargo and people. More strength helps, but the current model already assumes you could have lots of observation pods and structures suspended from the ring for commerce and tourism. The view would be amazing, 400 miles or 600 kilometers in any direction. And again, a simple parachute built in one would allow it to safely drift down in event of accident or sabotage. Indeed, people in pressure suits could probably skydive down from them, adding tourist revenue. Current cost assumes about $10 a kilogram for launch to orbit, cheaper just to go up the ring for a visit or around it and back down to travel to another city. In terms of building up there, since you're adding a new weight and presumably new solar panels to add and maintain power, even though solar is a lot better at this altitude, it is still pretty pricey, $110 a kilogram of static load. So building a 10-ton lightweight restaurant pod up there would run you $1.1 million in early 2022 money, a 20-ton RV equivalent $2.2 million, etc. Obviously that's still pretty small for living 3 times higher than the tallest mountain peak, or running a hotel or a restaurant there, and this baseline ring would be expected to be serving tens of thousands of people at a time. You can also overlap rings much as with the Orbital Ring to allow transfers between them. And as with them, your travel time once on the ring to anywhere on Earth is on order of a few hours, but getting up and down the tethers or elevators and to and from the stations they're anchored at is likely to match modern travel to airports and taxi, takeoff, and climb speeds, plus customs and security. So way faster intercontinental travel, and bigger versions of these might have bullet trains that left a ground terminal and stopped at another without pause at waypoints and averaged hypersonic speeds for the trip. It is a space launch system, of course, and that's its big interest to us, but that's the simple part. You electromagnetically accelerate the launch vehicle down a track once you're up there, skip beyond rocket fuel issues, and it just lets go and flies into space. You can launch at higher speeds and from higher altitudes if you want to send people and payloads directly to other planets without refueling. Alternatively, if you want to keep the capital cost of the Tethered Ring low, you could construct one that is closer to the ground, use it to accelerate vehicles just partway up to orbital speeds, and make up the rest of the Delta V needed for the mission with a second stage rocket or a skyhook. See our skyhooks episode for more details on those, and the Mass Drivers episode for more discussion of the specific mechanics and economics of electromagnetic catapult launches themselves. But not only does it let us get to space, it makes on-planet point-to-point travel much cheaper and faster, which is also the big selling point of the Orbital Ring. As with those and space towers and mass drivers, they can all be mixed and matched together to form a vast orbital skybridge network, allowing millions of people and millions of tons of cargo to move anywhere on a planet or into orbit or down from orbit every day, and at a cost equal to or less than modern transport costs, at a fraction of the time, and being purely electric via renewable solar or nuclear energy sources. Sounds like something worth building to me, or at least prepping for a prototype of. And again, the full 100-page white paper and technical specs are all available at the website listed in the episode's description if you want the nuts and bolts, projectatlantis.com. That's Project-Atlantis. Now, as I mentioned near the beginning, the active support here, in a way, is just keeping the ring rigid, and with a sufficiently advanced material technology, you could just have a giant solid ring tethered to a planet, hanging there for all time, unpowered. Also, for folks who ask about high gravity being a possible Fermi paradox solution, keeping people from space because rockets couldn't do it, this is one of those counter-arguments. The ring fabrication process lets you place it partially sunk under the ocean during fabrication as it comes out of a factory to avoid interfering with seagoing traffic while under construction. Then you turn it on and lift it under its own power out of the ocean and into the stratosphere. You can use it to bootstrap your orbital rings and other higher infrastructure into space too. Again, it's a great complementary technology of many we have elsewhere discussed, not just replacement or alternative. It works well alone or in tandem with other systems. So it gets us into space, but close out. Where else in space would we use it? Well, it works fine on a place like Mars or the Moon, though on the Moon it would be a bit redundant. We already have material strong enough for a classic space elevator on the Moon, and we don't need an elevated track to get us over its atmosphere, as it has none. So a simple raised track above the ground to allow a nice even circle can achieve the same job. It potentially works on Venus quite well, in tandem with cloud cities, or even augmenting them, but your tether material needs to be able to handle high temperatures since you are tethering into the ground, and Venus is ultra hot, but the melting point of carbon fiber is a lot higher than even Venus's inferno-like temperatures, so it's just making sure your anchor system, which is likely to involve a winch for loosening or tightening the tether, can handle the pressure and temperature there. You can't really use a tethered ring on the surface of a gas giant, and an orbital ring is preferable there anyway. Again, they don't really serve a function on any moons too small to have atmospheres, though they would be handy on Saturn's moon Titan. Also, they are great options for any world with significant gravity and atmosphere, especially ones where either is higher than on Earth. So a lot of options for use off Earth, and for getting us off Earth, and for getting us around Earth. Not bad for a simple tethered ring, and pretty impressive for an object that so counterintuitively hangs itself over the ground by hanging itself off the ground. One of the trickier parts about today's concept was trying to explain how the tethered ring avoids falling to the ground. And this same sort of problem comes up when folks try to figure out why a kite stays up, tethered and pushed and pulled on by wind and gravity, where the wind and lift is our active support in that case. Same problem of course for wondering why clouds stay up, or astronauts do, and many folks might shrug and just accept that they do, even if it seems counterintuitive. But if those sorts of things bug you and you want the tools to understand it better, then I would recommend Brilliant. Brilliant's focus on interactive learning, like their scientific thinking course on balance and center of mass, help illustrate concepts like opposing and balancing forces while letting you adjust the system and see the results. Many topics in science can seem hard because there is no interactive and intuitive way to work with the idea, compared to more traditionally hands-on topics that you can play with, and thus learn easier. So Brilliant focuses on making interactive and hands-on content, which makes it easier for anyone to learn, be it the basics or advanced materials like astrophysics. A better knowledge of math, science, and computer science can not only be enlightening personally, but a road to greater personal success. Be a lifelong learner, and let Brilliant be your partner on that journey. With Brilliant, you can learn at your own pace, learn on the go, and learn something new. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So this was the first launch system we've done a dedicated episode on in a while, and we may take a look at some others going forward, as I'm glad to say there's been a lot of good development on many of these with the renewed push to space we've had building up in this last decade. Part of what made this episode possible, though, was a great deal of technical and graphic aid from the Atlantis project, and I want to thank Phil Swan and Ceana Prado for their help in particular, and they both have long and distinguished careers in the aerospace industry, which lends the project more firm details than we sometimes get to have in our discussions of megastructures. And again, that website is linked in the episode description and has a number of additional explanations and technical details for those wanting an even deeper dive. It's always neat to work with experts, and one of my welcome perks from doing the show. And while I'm at it, I want to give a shout out to our longtime cover artist, Jacob Greiger, who has been making those great covers and thumbnails for the show since around episode 20, today being episode 359, not including bonus episodes. You may have noticed that we've been experimenting with covers a bit of late, and a lot of that has to do with me feeling that plastering the episode titles all over Jacob's amazing art when the title is already next to the episodes anyway was obscuring those needlessly. Now hopefully you can see his art better, and don't forget to check out his link in the episode description to see those in higher detail along with tons more of his art. And while I'm thanking folks, let me give a shout out to Sergey Cheremisinov, whose song Sirius is the one we always open and close the Outward Bound series episodes with, and we haven't done one in a bit, so it's nice to have a return. He's got an amazing collection of compositions I highly recommend. Speaking of returns, we have our monthly Sci-Fi Sunday episode coming up this weekend on alien imposters and doppelgangers, and we will be picking our SFIA Book of the Month, so make sure to join us then. And after that, we will be celebrating the 8th anniversary of our original episode, Megastructures in Space, by examining the barriers to becoming a Kardashev civilization. Then we'll continue September with a look at post-science civilizations, who have discovered everything there is to know or abandoned future research. And then, onto the grabby aliens perspective of the Fermi Paradox, and what grabby aliens are, and if we'll become an example of them. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website isaacarthur.net for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.